Microcontrollers such as Arduino and Raspberry Pi are common solutions where advanced robotic control systems are required. However, control systems such as these are ill-suited for use in industrial settings where any number of environmental hazards can do serious damage to these systems. By utilizing a variety of alternative control systems with a robust programmable logic controller, or PLC, at their center, an equivalent level of automation can be achieved, optimized for industrial settings. The automated sorting system here demonstrates such a control scheme, combining multiple systems compatible with high-hazard environments to accurately move products. The simulated industrial platform here consists of three primary subsystems. First, a PC-controlled robotic arm responsible for delivering product to the conveyor belt. Second, the conveyor belt itself operated via independent power distribution system in tandem with the PLC. And finally, the sorting system, which is comprised of a sequence of sensors and actuators controlled by an Allen Bradley Micro 820 PLC. These sensors include both infrared rangefinders, acting as height sensors, and a series of pneumatic pistons, which serve as linear actuators.
Figure 1 under the methodology section is the PLC sensor actuator subsystem diagram. The outputs for this system are the height A and height B linear actuators, the process running, process stopped, and system idle indicators. The inputs for this system are the height A and height B sensor, as well as the run process and stop process buttons. Figure 2 is the ladder logic program for the PLC that controls the sensor actuator subsystem. Figure 3 is the Wokata MyRobot robotic arm that's used in this project, and Figure 4 is the original 3D design. The results section includes the complete process flowchart as well as photos of the final product. In the upper left-hand corner is the flowchart for the robotic arm process. This process begins with the arm picking up a product by engaging a pneumatic gripper, then it moves the product to the conveyor belt, it releases the product by disengaging the pneumatic gripper, then it returns back to the pickup position. To the right of this is the product sorting process. If the green button is pressed, the system powers on, which activates the sorting process. This also turns the green LED on. Within the sorting process itself, if the height A sensor is engaged, a yellow LED turns on. This also energizes a solenoid, and a pneumatic valve opens and the product is pushed to bin A. If the height B sensor is engaged, a red LED turns on, the solenoid is energized, and the pneumatic valve is open and the product is pushed to bin B. If the red button is pressed, the system powers off. Beneath the flowcharts are photos of the full system. Depicted are the robotic arm, the conveyor belt, the sensor actuator subsystem, as well as the LED tower.
This automated robotic factory model is a great base for a factory sorting system. To improve its capabilities further, color and weight sensors could be implemented to sort by color or to activate the arm when a weight is sensed on a platform. Another functionality that could be implemented is the use of Modbus to communicate the robotic arm with the PLC. This would make everything conveniently controlled by one system. The PLC allows for easy control of various sensors, so the factory model could do a lot more with its sorting algorithm if given the time. Lastly, we want to give a big thank you to Dr. Vita Vakilian and Dr. Reza Abdali for their advisement in this project. Thank you to Jacob Gelman and Andrew Herdering for their assistance with our machinery. And lastly, thank you to Mr. and Mrs. Brown for their generous donation. Without you, this project would have not been possible.